Welcome back. In this video, we are going to learn to derive heat conduction equation in one dimension by applying energy balance, that is energy conservation law, across a finite element of finite thickness with some arbitrary cross-sectional area, and then use this equation to generalize the result for three dimensions. And finally, we are going to learn to reduce heat conduction equation in one dimension using given conditions of steady state, no heat generation, and constant cross section of the finite element, that is considering case of heat conduction through a plane wall. Since we are going to use this question as a learning reference, which is from GATE 2013 MEZA, let's first read out this question and try to analyze and understand it, what is given and what is asked. Consider one-dimensional steady-state heat conduction without heat generation in a plane wall with boundary conditions as shown in the figure below. Alright, so we have a case of a plane wall in which heat conduction occurs in one dimension in a steady state condition. Also, no heat generation occurs within the plane wall. Alright, also the temperatures on the left side of the wall is T1 and on the right side of the wall is T2, with T2 is greater than T1. Alright, let's proceed further. The conductivity of the wall is given by this expression, where K0 and B are positive constants and T is the temperature. Alright, now moving further, as X increases, that is, this position X increases, the temperature gradient will. Alright, so basically what this question is asking is that how does this temperature gradient varies, alright, as X increases. And one of the given information is that the thermal conductivity of the wall material is not constant, rather it is a function of temperature and is given by this expression. Alright, let's begin by considering and drawing a finite element of finite thickness delta x and cross-sectional area A at some spatial position x within a given body, such as this plane wall. Alright, so we have a finite element of finite thickness delta x at a spatial position x. The cross section of the finite element is A. Alright. In this diagram, the spatial direction x also represents direction of heat conduction through the considered finite element for our one-dimensional case of heat conduction, and the material properties of the considered finite element are density rho, thermal conductivity K, specific heat C, and volumetric heat generation rate dot Egen. Alright, so the spatial position x, this direction, also represents the direction of the heat conduction. Alright, and this makes our heat conduction case one dimensional because heat only conducts in the direction, meaning in the direction of x. Alright, the spatial position x. In other words, the heat only conducts perpendicular to the cross section of the considered finite element. Alright, and these are the material properties of the considered finite element. Let's suppose that heat at a rate of dot qx enters into the finite element on its left side in the spatial direction x. Alright, so we assume that heat at a rate of dot qx enters into the finite element in the spatial direction x from its left side. Alright, similarly, let's suppose that heat at a rate of dot qx plus delta dot qx exits the finite element from its right side in the spatial direction x. Alright, so heat at a rate of dot qx plus delta dot qx exits from the finite element from its right side in the spatial direction x. Alright, if we assume that the temperature of the finite element is T at a particular time T, then after a time period of delta T with time becoming T plus delta T, the temperature of the finite element would become T plus delta T, that is, temperature rises by delta T. In other words, after a finite time difference of delta T, the temperature of the finite element changes from T to T plus delta T, where delta T is the finite increase in the temperature of the finite element. Alright, and this rise in the temperature of the finite element is due to the fact that it receives heat at a rate of dot qx and it expels heat at a rate of dot qx plus delta dot qx. Also, it generates heat at a rate of dot e gen within it, alright, over its entire volume, alright. So, this rise in temperature of the finite element is caused by the finite heat capacity of this finite element, and this finite element receives heat at a rate of dot qx and expels heat at a rate of dot qx plus delta dot qx, and simultaneously it generates heat at a rate of dot E gen within its entire volume. So, the interaction of all these with the finite heat capacity of the finite element causes the rise or the change in the temperature of the finite element by delta T over a time period or a time difference from its particular time t. Therefore, since the finite element has a finite heat capacity, this finite heat capacity receives heat at a rate of dot qx and rejects heat at a rate of dot qx plus delta dot qx with internal heat generation, alright, causes the change or rise in its temperature by delta T over a time period or a increase in a time by delta T. Alright, now we are going to apply energy balance, that is energy conservation law, to the considered finite element, and according to the energy conservation law, the net or total heat gain by the finite element over a time period of delta t is equal to the change or increase in the internal energy of the finite element. Right. So the net or total heat gain by the finite element is equal to the change in the internal energy of the finite element. Right. We know that the net or total heat gain by the finite element is equal to the sum of the overall heat input into the finite element and total heat generation within the finite element, that has a volume of V over a time period of delta T. Now let's move to the next page. Since the finite element gains heat at a rate of dot qx and expels heat at a rate of dot qx plus delta dot qx, the overall heat input into the finite element over a time period of delta t is equal to this expression. Alright, because the rate of heat transfer is the heat transfer per unit time. So the overall heat input into the finite element is equal to the overall heat input rate times the time period. Alright, so this gives the overall heat input. Alright, since volumetric heat generation rate within the finite element is dot E gen, the total heat generation within the finite element of V over a time period of delta t is equal to this expression, because volumetric heat generation rate is the heat generation per unit time and per unit volume. So the total heat generation within the finite element is equal to the heat generation rate times total volume of the finite element times the time period. Alright, now we know that the sum of this expression and this expression is equal to the net or total heat gain by the finite element. So we would plug the sum of this expression and this expression into the equation 1. Alright, on the left side. Alright, so after plugging in the sum of this and this expression into the equation 1, we get this expression. Alright, if we assume that the mass of the finite element is delta m, which is equal to rho times v, where v is the volume of the finite element and is equal to A, which is the cross-sectional area of the finite element times the finite thickness of the finite element, which is equal to delta x. Then the change in the internal energy of the finite element when its temperature changes by delta t becomes as delta m times c times delta t, where c is the specific heat of the material of the finite element. Alright, so now we will plug in the expression of the change in the internal energy into this expression. Right, right. So after plugging in the expression of the change in the internal energy of the finite element into this expression, we get this expression. All right. Now we will plug in the expression of the mass of the finite element, which is equal to rho times b. All right. Now we will simplify this portion of this expression by cancelling the same terms and multiplying the negative sign through this bracket. All right. Right, so we have the simplified expression. Now we will divide this expression on its both sides by b times delta t. All right. So after dividing this expression by b delta t, we have this expression. Now we will simplify this expression and will write the next step. Alright, so after simplifying this expression, we get this expression. Now we will plug in the expression of V, which is equal to A times delta X. Alright, because the volume of the finite element is equal to its cross-sectional area A times its finite thickness, which is delta X. So we will plug in the expression of V into this expression and we'll write the next step. All right. So after plugging in the expression of V, we get this expression. All right. Since the thickness of the finite element is finite, temperature T within the finite element and its cross section across its whole thickness cannot remain unchanged. Therefore, to assume the temperature T and cross-sectional area A unchanged across whole thickness of the finite element, we will have to change the finite element into differential element. In other words, the thickness of the finite element becomes infinitesimally small, that is delta x, approaches 0, then the thickness delta x of the finite element can be replaced by differential thickness del x. Similarly, if the time over which the temperature of the finite element changes by delta t becomes infinitesimally small, that is delta t approaches 0, then the change in time can be replaced by differential time del t and the corresponding finite change in the temperature delta t of the finite element, which now becomes differential element, can be replaced by differential temperature del T with finite rate of heat transfer delta dot qx becoming differential rate of heat transfer del dot qx. Alright, so we will replace delta, which represents finite difference, with the del, which represents a differential change. Alright, in this expression, and we'll write the transformed expression here. Alright, after replacing the delta with the del, we have the transformed partial differential equation. Alright, since dot qx represents the heat conduction within the considered element in the spatial direction x, we are going to apply Fourier's law of heat conduction here, which says that the rate of heat conduction in a solid is proportional to cross-sectional area, thermal conductivity, and negative of the temperature gradient with respect to the spatial position perpendicular to the cross-sectional area, where the negative sign represents that the temperature T decreases with the spatial position x. Alright, now let's move to the next page. Now, using the Fourier's law as stated in the previous page, we will replace dot qx with this expression in the expression 2. Alright, alright. So after plugging in the expression of dot qx into the expression 2, we get this expression. Alright, now we will simplify this term and rewrite this expression in a more simplified form. Alright, so after simplifying this expression, we have the heat conduction equation in one dimension, which is a partial differential equation where A is the area perpendicular to the spatial position x. Alright, now we can generalize this result and obtain heat conduction equation for rectangular coordinates or Cartesian coordinates in 3 dimensions by adding 2 more terms on the left side, which will represent heat conduction in the y and z directions. Alright, So this term represents heat conduction in the x direction. All right, and we will add two terms similar to this term, which would represent heat conduction in the y and z directions. All right, whereas these two terms would remain unchanged. All right. All right, so we have the heat conduction equation in rectangular or Cartesian coordinates in 3 dimension. All right, where the areas such as A by Z represents the area perpendicular to the spatial position or x direction, and same here, the area xz represents the area perpendicular to the y direction. Also here, area x by represents the area perpendicular to z direction. All right, if the cross-sectional area perpendicular to any coordinate direction does not change, and if the thermal conductivity of the material remains constant, then we can simplify this heat conduction equation for rectangular coordinates in 3 dimensions. Alright, so if the cross-sectional areas perpendicular to the coordinate directions remain unchanged or constant, then we can cancel out these areas. Alright, and if the thermal conductivity does not depend on any spatial position or temperature, then we can take out thermal conductivity outside of the partial derivative. All right, and we can write a more simplified heat conduction equation for 3 dimensions in rectangular coordinates. All right, all right. So after simplifying this heat conduction equation, we have its more simplified form. Right. Now we will further simplify this partial differential equation and then rearrange it into a more standard form. All right. All right. After further simplifying this expression, we have this expression. All right. Then we further simplified it and divided this expression by k and get this expression, which is a standard heat conduction equation in 3 dimension. All right. Now we will consider heat conduction equation in 1 dimension that we have derived earlier. All right. Now we will apply steady state condition, which means that the temperature T does not change with time T at any particular location within the considered element, that is del T divided by del T becomes 0, and other partial derivatives in the heat conduction equation become exact derivatives as temperature becomes independent of time t and only depends on the spatial position x. Right, so we will set this term to 0. Alright, which will make this whole term 0. And by doing so, this partial derivative and this partial derivative will become exact derivatives. Alright, alright. After setting this partial derivative of temperature with respect to time to 0 and changing the partial derivatives to exact derivative, we get this expression. Alright, since it is given that no heat generation occurs within the given plane slab, we will set dot E gen to 0. Alright, we will set this term to 0 because there is no heat generation within the given plane slab. Alright, also as the cross-sectional area A of the plane slab does not change, we can take out A from inside the derivative. Alright, and then we will write a more simplified form of this equation. Alright, alright, after setting this term to 0 and taking out A from inside this derivative, we get this differential equation. Now we would further simplify it by cancelling out A from both the denominator and numerator. Alright, and we'll write the next simplified form of this differential equation. Right, so after simplifying this differential equation, we get this differential equation. Alright, now when we look at this differential equation, we see that the derivative of this term with respect to x is 0, which means this term must be a constant. Alright, so we can assume that this term is a constant because we know that the exact derivative of a constant is always equal to 0. Alright, so we will set this term to a constant C naught. Alright, alright, so the solution of this differential equation is this term is equal to some constant C naught, and we can assume that this constant is a positive one. Alright, now we will rearrange this equation and obtain the temperature gradient. Alright, so after rearranging this equation, we get this expression of the temperature gradient. Now we will plug in the expression of the thermal conductivity of the plane slab as given in the question, and we'll write the next step. Alright, after plugging in the expression of thermal conductivity K, we get this expression. Alright, and from this expression we can see that since the question asks whether this temperature gradient remains constant, increases or decreases as x increases. Alright, so from the page 1 we can see that in this given diagram that as x increases, the temperature within the slab also increases because T2 is greater than T1. Alright, so as x increases within the plane slab, the temperature increases from T1 to T2. Alright, so x and temperature both increase simultaneously. Alright, within the plane slab. Now let's go back to the page 3 where our expression is. So as x increases, the temperature also increases. Alright, and we know that both k naught and b are positive constants, so this denominator increases with x. Alright, and this whole term will decrease as x will increase. Alright, so this temperature gradient will decrease. Alright, so in a simple term, that as x increases, temperature increases. Alright, and this denominator increases, which causes this term to decrease because C naught is a some positive constant. Alright, so this temperature gradient will decrease as x increases. So let's go back to the page 1 and see which option is correct. Right, the question asks as x increases, the temperature gradient will decrease. Alright, so the correct option is option D, because we know that as x increases, temperature increases. Alright, and from our expression in the page number 3, that as temperature increases, the temperature gradient decreases. Alright, so the option D is correct, that temperature gradient decreases as x increases. Alright, now let's go back to the page number 3. Here, this expression which is a heat conduction equation in one dimension, is an important one, and we will use this equation directly in our future videos to address other problems of heat conduction. All right.